Now I will be discussing on the humidification and air conditioning. The syllabus is basic concepts, adiabatic saturation temperature, then humidification and dehumidification operations and design calculations of cooling tower, then mechanical draft towers, forced draft towers and induced draft towers, key points in the design of cooling tower and step by step design procedure of the cooling tower, and last point is air conditioning with some example problems and on the dehumidification. Most of the chemical industries use a lot of water for cooling purposes. Metallurgical plants and rolling mills also use a large amount of the water for their cooling streams. And however, the largest users of the cooling water are the power plants, in which a huge quantity of the low pressure streams from the turbine in condensed is in big condenser. So, cooling of warm water is done by direct contact with air in the cooling tower, and water is fed from the top of the cooling tower, whereas this air is blown from the bottom of the cooling tower, and the water enters through these louvers of the cooling tower. Evaporative cooling of the water occurs on the towers, the latent heat of this vaporization being supplied mostly by the water itself. So, before entering into the humidification operation and cooling tower design, as well as this dehumidifier, or we can say this air conditioning system, we should know some basic terminologies which are related to the humidification operation. The first term is we can say temperature, the second term is we can say humidity, and the third term is the enthalpy. And so, when a gas is brought in contact with a pure liquid in which it is essentially insoluble, then interface mass as well as this heat transfer take place. The term humidification is used to characterize this in a general fashion. Four major applications of the humidification operations are as follows. The major operation, that is humidification of gases for the controlled drying of wet solids. Mostly it is used for the drying of the food grade products. Then dehumidification and cooling of the gas in the air conditioning machine, and the third one is this gas cooling with the help of this water, and the fourth one is this cooling of liquid before this reuse with the help of this cooling tower. In terms of this, we can say temperature, there are two different types of temperatures. First is dry bulb temperature and second one is this wet bulb temperature. See, dry bulb temperature is the true temperature of the air measured by a thermometer whose bulb is dry as well as this bulb is bare. But in case of this wet bulb temperature, it is the steady state temperature attained by a small amount of evaporative water in a manner such that the sensible heat transferred from the air to the liquid is equal to the latent heat required for the evaporation. In wet bulb temperature measurement, the bulb is wrapped with this one wick and it is dipped in water, and when the steady state is attained, that time the some amount of the liquid water is evaporated and the wet bulb temperature is obtained. Then we need to understand about the relative humidity. So, it is the ratio of the partial pressure of water vapor in air at a given temperature to that of the vapor pressure of the water at the same temperature. So, we can say this on percentage relative humidity is equal to the Pa by Pa naught into 100, but we need to remember that relative humidity is not the explicitly the content of the water vapor in a gas, but it gives the degree of saturation. If we say that relative humidity is 80%, it means that the how much humid the air is compared to the other this one air, where we can say this relative humidity is less or more. And another term we need to understand, that is absolute humidity, or simply we can say this one humidity. It is the direct measurement of the moisture content in a gas. The mass of the water vapor per unit mass of the dry gas is called this absolute humidity. It is designated at y prime, that y prime is equal to Pa by P minus P naught Pa into 18 by 28.97 into 100. So, from here we can understand that how much amount of water vapor is there per unit mass of the dry gas. So, it is also called as Gross-Venner humidity, because the scientist Gross-Venner has first used this term, this absolute humidity. Now, this percentage humidity or percentage saturation, it is the ratio of the absolute humidity to that of the saturated humidity at the same temperature and pressure. So, that is why we can say percentage humidity is equal to y prime by y s prime into 100. So, where this y prime is the absolute humidity, or we can say and y s prime is the humidity at the same temperature and pressure if saturated with the water vapor. So, that y s prime is equal to this Pa nu by Pa nu into 18 by 28.97, and vapor pressure of the water can be calculated using this Antoine equation, where we can say this ln Pa nu is equal to 11.9648 minus 3984.92 divided by T minus 39.97, where we can say this one pressure will be in the bar and temperature will be in the Kelvin. Then this another important terminology we need to this one understand, that is the dew point. The dew point is a temperature at which a vapor gas mixture must be cooled at the constant humidity to become saturated, and at that point we can say this one first dew drop will be appearing. The dew point of a saturated gas equals the gas temperature. So, if vapor gas mixture is gradually cooled at a constant pressure, the temperature at which it just becomes saturated is also called its dew point. And another important terminology we need to understand, that is humid volume. That humid volume itself indicates that what is the volume of the this one, what is called mass of the dry air per unit, we can say this one accompanied at a particular temperature and pressure. So, that is say Vh is equal to 1 by 28.97, that is we can say the molecular weight of the air, plus 1 by 18.02, that is the molecular weight of water, into 22.4, that is the volume of 1 molar gas at an NTP, into Tg plus 273 by 273, where Tg is the we can say this gas temperature in degree Celsius. That is why 273 is added with Tg. Another terminology we need to understand, that is humid heat. That humid heat is, it is designated as Ch, is the heat this energy required to raise the temperature of unit mass of the dry air with accompanying water vapor by 1 degree. So, that Ch is equal to 1.005 plus 1.88 into y prime. The first part of the right hand side, that is 1.005, is the heat capacity of the dry air in kilojoule per kg Kelvin, and the second part, that is 1.88 into y prime, is the heat capacity of the water vapor. So, this overall we can say this one humid heat of this moist air. And the last term, that is enthalpy. The enthalpy of a vapor gas mixture is the sum of the relative enthalpy of the gas and the vapor, the content. So, H prime is equal to, we can say the Ch into Tg minus T0 plus y prime into lambda 0. That is, if we just replace this first term of the right hand side, that is will be equal to 1.005 plus 1.88 into y prime into Tg minus T naught plus 2500 into y prime, where this lambda 0 is equal to latent heat of evaporation of water, that is 2500 kilojoule per Kelvin kg. Now, we will be learning another important terminology, that is adiabatic saturation temperature. So, before understanding this adiabatic saturation temperature, we will be discussing on the one adiabatic container. This one chamber is maintained adiabatically, means no heat is taken inside this chamber, or no heat is lost also from the chamber, or we can see this, it is encircled with this insulated wall. And say from the right hand side, suppose air is entering this one through, we can say this one through this air is entering at Tg, or we can say the gas temperature with humidity is y prime, and this one water is, we can say, the spread from the sprayer inside this, we can say, humidification chamber, and this the entire chamber is maintained at, say, let us say TAS. We say this one temperature as TAS, and the again water is recircled to the, we can say this one, from the chamber again to the chamber, and say some amount of this air is, we can say this one is coming out at TAS, because our target is to maintain this entire chamber this one at the temperature of TAS, and that time this, we can say this one, humidity will be increased from y prime to ys prime, and as some amount of water will be evaporated during this, we can say this one, during the maintaining the entire temperature at TAS, some amount of water will be evaporated. That is why some amount of makeup water is fed at TAS to maintain the temperature of the entire chamber at TAS. So, that we can say this one, the temperature TAS is called this adiabatic saturation temperature. We will be discussing in detail about this, that temperature, that what is really the adiabatic saturation temperature. So, you see this, whenever the enthalpy in with this air inlet, that is, we can say this one, that will be like H I prime is equal to C H into T g minus T A S plus lambda s into y prime, because this air will be in at T g temperature, and the difference in the temperature will be T g minus T A S, and the enthalpy of the exit air from here, actually what is coming out, that is H O prime is equal to C H into T A S minus T A S, because that is ultimately it is converted into the temperature is attained at T A S plus lambda s into y s prime, because that time we can say this one, humidity has increased from y prime to y s prime. So, at steady state we can say this one, whatever the enthalpy in and whatever the enthalpy out, both will be same. So, we can say this one H prime I is equal to H prime O, and hence we can say this one, from these two equations, this equation and this equation, we can say C H into T g minus T A S plus lambda s into y prime will be equal to lambda s into y s prime, and from here we can say this one, T g minus T A S is equal to lambda s by C H into y s prime minus y prime. Just by manipulation we have arrived at this T g minus T A S. This T A S actually is called adiabatic saturation temperature, where this T g is this gas temperature, or we can say this one, this dry bulb temperature, that is the temperature of the air, this one in the dry condition, or without any, we can say this one saturation. Now, you see this one, we need to understand the meaning of this wet bulb temperature. Previously also I told that, say, whenever this lamp of this bulb, or we can say thermometer bulb, is wrapped with this any cotton, or we can say this one any cloth, and it is dipped in water, and say some amount of water actually evaporated, that time we can say this one, if the vapor pressure of the water is higher than the partial pressure of the water vapor in the ambient air, then evaporation will take place. So, latent heat of evaporation will be supplied by the surrounding air and water drop itself. So, now we need to consider one say drop of water at the tip of thin wire. Suppose one water drop actually is hanging, one water drop is hanging from the thin wire. So, as the temperature of the water drop decreases, actually with time vapor pressure decreases, causing a reduction in the partial pressure driving force, and temperature driving force for heat transfer from ambient air to water will increase. So, if sufficient time is allowed, a steady state temperature will be attained by the drop, and then we can say this one, this is actually wet bulb temperature, or in other words we can say this one, whenever one bulb is wet with this water and say it is about to evaporate, that time whatever the temperature of the bulb will be showing, that will be wet bulb temperature. So, the factors that influence on the wet bulb temperature will be first the wet bulb dry bulb temperature of the air, that is Tg. If Tg is high, then we can say this one, the wet bulb temperature will be high. If we can say this one, humidity is high also, then we can say this, if humidity is high, then we can say wet bulb temperature also will be high. If the air velocity is very high, very fast, then we can say this one, then wet bulb temperature will be very low. The shape of the thermometer bulb means if it is spherical, then this one we can say this one will be getting more surface area to be evaporated easily, because this we know that evaporation is the surface phenomena. It is dependent on the how much amount of space is available. That is why we can say this one, so many factors are there that influences the wet bulb temperature. So, for a particular Tg, or we can say this one dry bulb temperature, wet bulb temperature will be different, means with wet bulb temperature may vary depending on the these above 4 situations. The combination of the dry bulb and wet bulb thermometer is called a psychrometer. It will be widely used in our calculation of the cooling tower, and also will be using this one during the drying operation also. Now, we will be determining the relation between the wet bulb and dry bulb temperature. So, suppose this the bulb is wet with this water, and say one film is formed with the help of the cloth or cotton like this. That is why this heat flux will be Q is equal to Hg into Tg minus Tw, where Tg is the this one what is called air temperature, and Tw is this water temperature, at which temperature the water is. Then molar flux, that is we can see this Na is equal to Kg into Pw minus Pa, this how much amount of water is evaporated from the bulb of the thermometer. Since the heat flux is sufficient to meet the requirement of the latent heat of vaporization at the steady state, we can say this Hg into Tg minus Tw will be equal to lambda w into mw into Kg into Pw minus Pa, that is nothing but lambda w into Ky prime into Yw prime minus Y prime. So, from there we can say Tg minus Tw is equal to lambda w into Yw prime minus Y prime by Hg by Ky prime. From there we can say this one, for any system Hg by Ky prime is equal to 1.23 into Smith number to the power 0.6, and now we can say this one from the two equations like Tg minus Tw is equal to lambda w into Yw prime minus Y prime by Hg by Ky prime, and Tg minus Tw is equal to lambda w into Yw prime minus Y prime by Ch. Both the equations are now we can say this one identical, means we can say this one Tg minus Tas is equal to lambda s by Ch into Ys prime minus Y prime, and Tg minus Tw is equal to lambda w into Yw prime minus Y prime by Ch. In both the equations you see Tas and Tw are equivalent, whereas we can say this one Ys prime and Yw prime both are identical. So, we can say this one Tas is equal to Tw, or we can say this one adiabatic saturation temperature and wet bulb temperature are nearly equal for air water system. And for other system maybe there will be a small variation, but for air water system we can say this one we will be assuming this Tas is equal to Tw, and this Tg minus Tas or Tg minus Tw is called this wet bulb depression. Now, we will be learning something about the psychrometric chart construction and its use. the 7 important quantities, like namely we can say this on dry bulb temperature, then wet bulb temperature, relative humidity, absolute humidity, dew point, enthalpy and specific volume are all interrelated. These are interrelated in the psychrometric chart. This so we say psychrometric chart characterizes this interdependency. If we know any two of the parameters, like say if we know dry bulb temperature and wet bulb temperature, or if we know this dry bulb temperature and relative humidity, or if we know this absolute humidity and relative humidity, or we can say this if we know dew point and dry bulb temperature, we will be able to calculate the other 5 parameters from the psychrometric chart for air water system. And we need to remember that the psychrometric chart is prepared at 1 atmosphere pressure. Now, you see psychrometric chart construction is very easy. Let us take this Tg at this point. Tg is equal to this, suppose this dry bulb temperature of the gas and this humidity is y prime. Then we can move to this point, up to this we can say this A percentage saturation, then will the junction point will be A. Now, you see this one adiabatic saturation line will be through A to B like this, because all the adiabatic saturation lines will be like following this line. Now, we will be reaching this point B, where we can say it is 100% humidity line. Okay. So, and if we move from point A to C, we will be getting the how much amount of humidity is there, that is called y prime. Okay. And this corresponding to B point, where we say this one it has touched this 100% humidity line. From there, if we go to this y axis, where we can see the humidity is there, that E point actually will be obtaining this E point, that is we can say this one it is adiabatically saturated air. And from B, if we move to this vertical direction to the temperature line, we will be getting this wet bulb temperature. Okay. And say from point A, if we just move towards this, we can say this parallel to the temperature line, if we reach this point D, or we can say this if it touches this 100% humidity line and corresponding temperature is called this, we can say this one corresponding temperature, we can say this dew point temperature. Okay. And say for this Tg temperature, or we can say this one dry bulb temperature, if we move to the vertical direction and whenever it reaches this we can say this one saturated humid volume line, then point F actually will be obtaining there, which is nothing but we can say this one in point F we can say this one that is the humid volume of the saturated air at Tg. And this one and another green line is there, that is we can see this one humid volume of the dry air, then we can say this it has touched at point G, that G is nothing but we can say this one the humid volume of the dry air at Tg. Okay. And you see this one enthalpy of the sample of the air also can be obtained by this one same way, because the enthalpy is measured or is shown in the y2 axis. So, whatever the value is there, corresponding value of the enthalpy will be obtaining from the y axis, y2 axis. Okay. And accordingly, you can say this one humid volume will be this one calculating or will be measuring from this y1 axis. Okay. So, this is the we can say this is a psychrometric chart of the air water system for 1 atmospheric total water atmospheric pressure. If we say this one, the whatever we discussed here this one in the previous this one figure, like this one in the previous figure like this is the actual you can see the psychrometric chart for air water system. If we take any of the temperature, like say if we take 80 degree Celsius as the dry bulb temperature, and if we say this one say percentage relative humidity, say let us say to 10% like this, then we can say we need to move from this point to this, then we will be reaching this point. then these are all, we can say this one, all these are adiabatic saturation curves, and whenever it will be reaching 100%, from here if we come here, we will be getting this, say around say 45 degrees Celsius will be wet bulb temperature. And from here, say as we mentioned that for 10% relative humidity, we can see the humidity will be like 0.05 will be the absolute humidity. Suppose from this 10%, say if we just move in the parallel direction of the temperature, from here we will be getting 40 degree Celsius as this dew point temperature. And correspondingly, we can see this one, enthalpy of the saturated air will be obtaining from this curve, and enthalpy of the saturated air will be obtaining from this curve, and specific volume, we can say this will be obtaining from the specific volume of the dry air will be obtaining through this curve, where it is like this one green in the previous this one figure. Okay. Now, we will be discussing about the humidification and dehumidification operation and the desired calculation. The humidification operation, in this operation we can say this water transfers from liquid phase to gas phase, hence moisture content of the air increases, and air with the particular moisture content is useful for drying of the solid under the control condition. Like for dehumidification operations, it is the reverse phenomena of the humidification. So, a portion of water vapor from moist warm air is condensed by the contacting cold water in the air conditioning system. So, now we will be learning about this cooling tower principle and the operation. A cooling tower is a special type of heat exchanger in which the warm water and the air are brought in direct contact for this evaporative cooling. So, we need to understand the meaning of this evaporative cooling, that during this evaporation some amount of the heat will be taken from this we can say this one water, and the due to that we can say this one transfer of the latent heat from the water for the evaporation, the we can say temperature of water droplet will go down. Okay. So, it provides a very good contact of air and this one water in terms of the contact area and the mass transfer coefficient of the water vapor, while keeping air pressure drop this low. So, enthalpy of the air is lower than the enthalpy of this water, that is we know. So, the sensible heat and latent heat transfer takes place from water drop to the surrounding air. Now, this is schematic of the heat transfer from water drop to the surrounding air is presented in this figure. From this figure, we can easily observe that this water drop is at TW temperature, we can see this water temperature, and air temperature is TW. This air temperature also is at TW, and heat transfer takes place from water drop to the surrounding. Okay. Thus, the cooling is accomplished by the sensible heat transfer from water to the air and evaporation of the small portion of the water. So, now one generalized cooling tower actually is shown here. The hot water which is coming from the heat exchanger is spread at the top of this cooling tower, then air enters through the louvers, or we can say this one air may enter from any of the sides of the cooling tower, and during this cooling process of the water around 2% water is evaporated, but for that makeup water is used to keep the system steady. So, makeup water actually used to compensate the water loss due to this evaporation, and blow down is there to drain a part of this water containing the solid deposit, because you see we know that say in most of the chemical industries, say maybe whatever water, hot water is coming out from there, some amount of the solid may be there, or sometimes in the cooling tower itself some amount of the fungal growth takes place, and some amount of the we can say this dust or darts are these are deposited at the bottom of this cooling tower, and these are actually blown from the bottom of this cooling tower, that is called blow down. So, that blow down amount of also is added with the makeup water. So, the exit cold water from the cooling tower is used in the heat exchanger or other unit operations like this, where this cold water is required for that is actually obtained from this cooling tower. That factors that govern the operation of the cooling tower, that is the dry bulb temperature and the wet bulb temperature of air, that is obvious, and the temperature of the warm water. What is the inlet temperature of the warm water? If the temperature of the warm water is very high, then we can say this one temperature of the cold water which will be exiting from the bottom of this cooling tower will be high also. The efficiency of the contact between air and water in terms of volumetric mass transfer coefficient. So, that is important, and how efficiently the air and water will be in contact. So, that we can say a good amount of both heat and mass transfer will take place efficiently, and contact time between air and water. If we can say this one water flow rate is very slow, then we can say we will be getting more contact time. Then uniformity of the distribution of the phases within a tower, that is also important, because you see inside this cooling tower in most of the cases the wooden louvers are also placed, and how uniformly the water is sprayed from the top through these nozzles, that is also important, and air pressure drop across this cooling tower. Then desired temperature of the cold water, that is sometimes we need the water to be this one to come out at a particular desired temperature, but sometimes we can say this one based on the above parameters, the temperature outlet of the we can say cooled water will be this one different from whatever we want. Now, we will be discussing about the types of the humidification equipment. So, based on this air draft, so we can say this one 3 different types of cooling towers are there. One is this atmospheric, another one natural, and third one is the mechanical draft. And based on this airflow pattern through the cooling tower, that is we can say this one cross flow, another one is counter flow. And in mechanical draft, we have these 2 different types of cooling towers. One is the induced draft, another one is this forced draft. So, first one is that is we can say this one atmospheric tower. It is a big rectangular chamber with 2 opposite louvered walls like this from the left hand side and the right hand side. We can say this one, all these are we can say this one louvers. Louvers are nothing but we can say this one water these wooden slots which are placed in the opposite side of this we can say this cooling tower, and water actually is sprayed through this we can say this one through this sprayer at the top of this cooling tower. So, tower is that is back to this we can see this tower fill, then atmospheric air enters the tower through the louvers driven by its own velocity. So, here actually no we can say this one fan or anything is used to draw this air through this cooling tower is provided. The direction and the velocity of wind greatly influence its performance. So, this figure shows the schematic of the atmospheric cooling tower. So, hot air actually will be out, say suppose air at this ambient temperature or we can say this on dry bulb temperature Tw is entering through here, and whatever the hot air actually will be out with the huge amount with the excess amount of this water vapor. Moist air actually will be coming out from the top of this cooling tower, and this water will be sprayed, and during this we can say this one from the top to bottom the some amount of the water will be evaporated. During this evaporation or we can say evaporative cooling, due to this evaporative cooling the water temperature will drop down and this cold water will be out from the bottom of this cooling tower. Then we have this natural draft towers. Say a natural draft cooling tower has a large reinforced concrete shell of this hyperbolic shape, also it is called hyperbolic tower also. Natural flow of this air occurs through the tower, hence it is called natural draft. This shape actually we can say this one gives this natural draft. In next slide we have this one, we will be showing the natural draft this cooling tower. The factors that are responsible for the creating the natural draft, that is first one is that a rise in temperature of and humidity of the air in the column reduces its density. So, from bottom to top actually it decreases the density, and wind velocity at the tower bottom. So, in the we can say this one at the bottom level, or we can see this ground level, the wind velocity will be higher, that is why it will be forcing to enter into the cooling tower. The fan, sometimes this fan is used to enhance the airflow rate in fan assisted natural draft towers. The typical diameter of the tower is we can say the 150 meter, and the capacity is we can say this one 5 lakh gallon per minute. So, this is the schematic of the natural draft tower, this cooling tower. So, you see this one air actually will be in through the bottom of this, we can say this one cooling tower, and hot water actually is in from this side, and we can say this one, and hot moist air actually will be out. As the shape of the cooling tower actually is, we can say this hyperbolic, that is why you can say this more packing material can be placed at the bottom, and the we can see the entering air gets smoothly directed towards the center, and greater structural strength and stability is obtained, because you see at the bottom, or you can see the ground level, we can see the surface area is more. And now we have this mechanical draft towers. There are two different types of mechanical draft towers. One is this forced draft cooling tower, and this induced draft cooling tower. So, fans are used to move the air through this tower in mechanical draft cooling towers. So, two types of, we can see this one, this is first one is this forced draft cooling towers. It has one or more fans actually located at the tower bottom to push the air into the we can say this tower, like this we can say this one air actually is in, the fan actually is there, and it forces air to enter through this, we can say this tower, and the entire tower actually is packed with this packing material, and these we can say this hot this one what is called water actually spread from the top of this cooling tower, and there is some drift eliminator. That is, we can say this one, during this spraying some amount of the drift of water, this one what is called droplet will take place, and to eliminate this one, some one type of, we can say this one grate is provided there, and say it eliminates the, we can say this one, or we can say this one, it restricts the water, we can say these droplets to be removed through this warm air, and these are actually now directed towards the packing material or towards the bottom of this cooling tower, and this cold water is coming out from the bottom of this cooling tower. So, the advantages of the we can see this forced draft cooling tower are like this: a part of the velocity head of air thrown by the blower is converted to the pressure head, because the air blower actually is used there on entering into the tower. It makes the energy efficient than the induced draft. So, that amount of, we can say this one, we can say this whatever the air is this one entering, that is, we can say it will be entering with this more pressure head. Okay. So, this we can say this one, it will be moving in a very high speed and less susceptible to vibrations as fans are installed near the ground. So, if the fan also is vibrated, then it will not affect the performance of the cooling tower, because it will not vibrate the cooling tower, because it is placed, it is not mounted on the cooling tower, it is mounted at the ground of the, we can say, where the cooling tower is installed. Maybe it is apart from the cooling tower, but some disadvantages also are there. So, airflow through the packing may not be uniform, because you see this one where the fan is placed within this area, suppose the air flow rate will be very high, but where the fan is not installed, there we can say this one flow rate of air will be very low. Some of the warm and humid air may be recirculated back actually due to that type of, we can say this one fan application. Some amount of the humid air maybe we can say this come back and it again it will be recirculated. So, recirculation rate becomes low if the wind velocity is very high. So, it is not popular actually except for small capacity like this. And then we have this second type, that is called induced draft tower. So, one or more fans are installed at the top of the tower. So, depending on the air inlet and this flow pattern, induced draft towers are of two types, like one is the cross flow, another is counter flow. So, major advantages of the, we can say this counter current induced draft cooling towers. There are say two major advantages. One is the relatively dry air contacts the coldest water at the bottom of the cooling tower, and another one is this humid air is in contact with the warm water, and hence the maximum average driving force prevails for both heat and mass transfer. So, these are we can see these are major advantages of the counter current induced draft cooling towers, but some disadvantages also are there in case of the induced draft cooling towers compared to the forced draft cooling towers. It consumes more horsepower, and cross flow induced draft cooling tower requires less motor horsepower than the counter current induced draft cooling towers. Now, we will be discussing about the cross current and counter current cooling towers. A cross flow induced draft cooling tower supplies actually horizontal air flow along the packed height and requires less motor horsepower than the counter current flow type cooling tower. So, additional cells may be added to raise the capacity. So, in the left hand side the schematic of the we can say mechanical draft counter current flow tower actually is shown here. You see the air is in from both the sides through the louvers, and the hot water actually is sprayed from the top, and at the top actually say drift eliminator is there, and say induced draft, the fans are used to take out these we can see this moist, warm and low density air to take out from the cooling tower. So, this is we can say this one mechanical draft counter current flow cooling tower. But in case of the mechanical draft cross flow this one flow cooling tower, so the we can say these airs will be in through the louvers from the both the sides, but you see this air is sprayed actually from the top, not it is not the continuous one. So, in one part it is suppose out of these two parts. So, in one part the water will be sprayed, and then induced draft this one what is called fans are installed in between these two parts of the we can say two parts of the cooling tower. So, whenever cold air will be in, and this will be in contact with water which are sprayed from the top, and it will be coming out from the we can say this through the we can say this drift eliminators, and these are we can say this one placed in the we can say this one vertically placed, not the we can say this horizontally. But in case of this we can say this one counter flow cooling tower, the drift eliminator is placed horizontally with the we can say this one packing materials. So, whenever the water the moist air will be coming out from the packing material, this will be like this. That is why we say this one cross flow, means this one water is sprayed from the top and air will be allowed to flow to the perpendicular to that of the water flow. That is why we say this one cross flow. So, in case of this cross flow this one mechanical draft cross flow towers cooling towers, we can add the we can say this one so many modules one by one. That facility is available for this we can say cross flow this mechanical draft cooling towers. But in case of this counter flow cooling tower, that is it has the fixed structure. So, we cannot add. So, we can say this one if this one we have the opportunity to use to select any of the cooling towers, say we should select this mechanical draft cross flow cooling tower, because in that case we will be able to add one module to the another one just one by one in the series we can place, and in that case we can see this as the cross flow this one what is called pattern is there for the water and the air. So, we can say this one, it has the better contact, and we can say this one, efficiency of the mechanical draft cross flow tower is much more higher than the, we can say this one, counter flow tower. Thank you. In the next class, we will be discussing on the cooling tower design by step procedure.